Good day and welcome to today's technical session of the CNPS. I'm Ian Cowan, and we're delighted today to be able to welcome back one of our stalwarts to the whole subject of alternative physics and theoretical physics, James Keene. He's spoken to us on a number of occasions and also reasonably recently. Now, I'm personally very grateful to Jim for having stepped in at short notice, owing to some cancellations we had at the last minute. So today we're filled with a talk. And by the way, I've kept to the conventional operations of the CNPS, and before that the NPA, where they tended to standardize on Eastern Standard Time, of the United States. So in other words, when the hour changed, which it did last week, we still kept to 10 hours Eastern Standard Time. Now that meant in other places the time would change. So for example, in Ireland, the hour doesn't advance until the end of this month. So I have to start an hour earlier. It's 2 p.m. now instead of 3 p.m. But most people in North America will find that the time has not changed, even though their clocks have gone forward. I hope that's satisfactory. Now, Jim has been working on this whole area of binary mechanics, which he has addressed us in connection with on many occasions before. And today he's looking at primary and secondary constants. The question is, how did binary mechanics derive physical constants? A true derivation of a fundamental constant value is based on first principles alone. So this is something Jim has mentioned a number of times, that some of these things come into other explanations of physical theories as fortuitous parameters or something. But he says no, they're fundamental and they're to be derived. In fact, in two descriptions of this, he gave things which are slightly differing. I think in the today's explanation, he says deriving primary and secondary constants, but then he also gave me a bit of a spiel where it said deriving primary from secondary constants. So we'll ask him to explain all that in a moment. Now he's going to commence with a short video. It's a new video which lasts about 15 minutes, and it responds basically to the frequently asked questions: how did binary mechanics derive these physical constants? A true derivation of a fundamental constant value is based on first principles alone. Very important. First principles, Jim says, not subsequent establishment of these figures as fortuitous figures, as I say, without any use of other fundamental constants, which are really unexplained. So that's the fundamental point, unexplained. And so we also have agreed that during that video, I'm actually inviting people to pose questions. I'll be keeping an eye on the chat and also the private chat. So Jim is very happy. In fact, he's encouraging this. He's very happy to stop this short video and maybe have a bit of a discussion and then recommence. So don't feel inhibited in that respect. If you have any questions about the video or about the subject that the video is bringing up, please make the comment and we'll stop the video. And then there's some comments coming in at the moment. Similarly, we're hoping to show another video which I think lasts about 33 minutes, and that's more on the BM, the binary mechanics equations and the mathematics of it. So again, that'll be a bit of it'll actually indicate how the simulator which he has available works, and indeed not only the simulator but the universe as a whole according to the theory. So okay, so without further ado, I think I should keep quiet now and add Jim to the stage. So I'm going to hand over to you, hello, Jim, and I'm going to put up your screen. You're most welcome, and again, my heartfelt gratitude for stepping in at such short notice to give us this most interesting talk.
I'm honored to be here.
So Jim, I put up your screen, and that will allow you to show this MP4 video, and indeed to stop it and recommence when you wish. So what I'm going to do is I'm going to disappear myself. I'll be in the background, but you'll have complete control. You'll have the audio. I will, in a moment, probably minimize your photograph. In other words, I'll get rid of it, so the screen will cover everything. But you will still be audible, and you'll have control. And if you want me to do anything, I'll come back. And with your permission, if people have these pressing questions, and you don't see them, I'll come in and I'll say, Jim, could we stop here? So if that's all right, I'll disappear now.
Okay.
Thank you. Thank you. The floor is all yours, Jim.
Hello. I'm often asked how the primary and secondary physical constants were derived at binary mechanics lab. The secondary physical constants are shown in the red box here below and are unexplained measurements, wrongly called fundamental constants. And these are used as input parameters in various theories, such as the standard model of particle physics, where there's some 20 or so values which are input parameters in order to make that theory work. That's very lame. General relativity uses the vacuum speed of light right there in the field equation. That's also very lame. It's sort of like you have to master arithmetic before you can do algebra. The vacuum speed of light, why it has the measured value that we observe, is like the arithmetic, and the algebra would be trying to explain phenomena such as the attraction of objects in gravity or what have you. Appendix A in almost any textbook is called fundamental physics constants, listing velocity of light, Planck's constant, electric charge, and so forth. And this is sold by obedient physicists as fundamental inputs required by incomplete, flawed physical theory. With multi-millions in research funding, the scientists appear very authoritative. However, the greatest body of unexplained observations in physics, think about that, the greatest body is the so-called fundamental constants. So Appendix A in your Physics 101 textbooks should say most important unexplained data in physics. News alert, Binary Mechanics Lab published first ever derivations of basic physical constants from first principle. Here are equations for the alpha coupling constant and the Bohr magneton, which express those values in terms of other so-called fundamental constants. The measured values of these so-called fundamental constants are not independent, as these equations show. They contain redundant information. If they didn't, you couldn't write these equations, which you see right before your eyes now. Therefore, these constants are not fundamental, and furthermore, they could not be fundamental. I'd like to add a point right here. Can you hear me okay?
Yes. Yeah,
the point I'd like to add quickly is that there's also an equation that shows light speed as being a function of the permittivity and permeability of space in terms of Maxwell's equations. But the permeability and permittivity are also basically observed measurements as well, at least so I would allege, and maybe that would be a point for discussion. I'll continue with the video now. If you understand what a simple algebraic equation is in fact saying, we might use an analogy to a video game in our adventure to derive the primary and secondary physical constants. We start the game located here between the orange box and full quantization in the green box. This is our wasteland, where for hundreds of years, even millennia, investigators have based their work on the assumption of continuous energy, space, and time. In recent centuries, the theory of continuous energy, space, and time included classical physics, special and general relativity, and outdated 20th century quantum mechanics. But this whole area of our game map has turned into sort of a wasteland where, for example, in the game Fallout 3, a weather report might be scattered mutilations with occasional dismemberment. So what we need to do is to venture into the postulate of binary mechanics, of full quantization of energy, space, and time. Now, we're going to have to dip into the unexplained measurements, wrongly called fundamental constants, to reverse engineer these secondary constants below to obtain primary constants above. Let's look at that. With the postulate of energy, space, time quantization, the next logical question is, what are the values for energy, length, and time? How do we determine the values for energy, space, or length, and time? Well, we're going to have to look at the measured values for the so-called fundamental constants shown in red boxes here in our physical constants derivation tree. We use certain guidelines to reverse engineer the unexplained measurements to discover the primary constant value. First, we use dimensional analysis. In the derivation tree, units of derived values must follow from the units of input values. For example, bit velocity has the units of length divided by time. Electron rest mass has the units of energy expressed in kilograms. Planck's constant, which comes from our elemental action A, contains an expression for energy, mass times velocity squared, and an expression for time, our primary time constant. In other words, the units for the Planck constant are joules second. Likewise, the units of elementary charge are energy length, or joules length. Second, we have theoretical constraints. Binary mechanics postulates imply specific limits and or constraints on possible values. An easy one is the speed of light. If you look at the spot cube model of space in binary mechanics, a unit of energy cannot just move in any arbitrary direction. It can only move out of that spot cube through the 6 faces of the cube. In other words, there's only 6 directions it can go. And so for a unit of energy to move from some arbitrary point to another arbitrary point, it has to take sort of a little bit of a zigzag pattern, usually, to get to the destination point. So that's a constraint. So therefore, we actually have electron contains 3 M-type quanta. And so therefore, to be consistent.
Jim, I'm sorry to interrupt. It's beginning to break up a little. Did you notice that?
The energy constant here must be items in the red boxes here. There are published, measured, observed values. Prior to binary mechanics, it was not understood.
Jim, can you hear me?
Why these quantities had the
I'm sorry.
measured values.
The video is starting to break up. Did you
Yes,
notice
Ian.
that? Yes.
Yes. What we might want to do, Ian,
is that you play the video and see if it doesn't break up.
Well, if you wish.
Does that make sense?
Yeah. That's assuming that there's some problem at your end. You're not recording or anything like that, Jim, are you?
No, I'm not recording, but it just means that apparently the system here is not perfect in terms of I've got a fiber optic cable connection, so it should be it's very, very fast. But on the other hand, it could be the service provider is having some glitches or whatever.
Right. Well, it's not that bad.
So,
what we could do, if you wish, is we could proceed. We're halfway through it, and maybe for the next video, you'll permit me to play it. What do you think of that?
Okay, fine.
Okay, if it gets
so
very
should
bad,
I continue now, sir?
Say again?
Should we?
Please proceed.
I'll continue then.
Please.
Observe. However, with those measured values, and if the quantities for and that should all agree, and all of this was set up in spreadsheets to calculate the values to confirm that these quantities were energy in kilograms, length in meters, and time in seconds. In fact, according to the equations shown here, give you the observed measured values. That is a critical point. Lastly, basic formulas in Physics 101 textbooks were applied where applicable. For example, to calculate angular momentum, it is the sum of the various energy quanta, which are what we call the bit cycles for the electron and the proton. So I think we're doing pretty good in our venture into the wonderful land of full quantization in binary mechanics. And our character hasn't had to use any health packs or stim packs because we haven't taken any damage. And so let's proceed. We've reverse engineered the secondary constants below and to obtain primary constants above. And then with those primary constants, we can calculate the unexplained observed values. Let's look at this quest in a little bit of detail. A series of papers document this second quest. We can do a quick walkthrough of the papers published in the Journal of Binary Mechanics, which establish that we can calculate from the primary constants of binary mechanics the measured observed values of the so-called fundamental constants, which I call secondary constants. First, we have zero electron electric dipole moment. Here is the electron quanta cycle, where the two types of energy quanta, shown by circles and arrows, revolve around a central axis shown by the gray dot here, which is perpendicular to the page. There is no collection of charge on one side or the other, and so the what we call the electron electric dipole moment is zero. And this agrees with findings of major labs, which have thought that the shape of the electron therefore must be like a sphere. But in fact, in binary mechanics, it's more like a spinning top shape. Unlike the electron, the proton has a non-zero electric dipole moment. It's sort of like a water molecule, where one side of the water molecule is more positively charged than the other side. That's what we mean by an electric dipole moment. This finding also agrees with experimental results from major labs. The electric charge positions can be viewed in sort of an X-ray fashion, where the dark red is plus and the yellow is minus charge. And you can see from these two views that the plus charge is more to one side of the proton and the negative charge is to the other side. Here is a detailed analysis of the positions of quanta in the proton bit cycle, which was used in this analysis. Next, we have the fine structure constant derivation, where the fine structure constant, the ratio of the scalar and vector bit operations, which involve electric for scalar and magnetic for vector, divided by the number of M-type quanta available to be accelerated by these two potentials, scalar and vector. That is the definition, very simple, in binary mechanics of the alpha coupling constant. Running the binary mechanics lab simulator, we find that the fine structure constant alpha varies somewhat when plotted against quanta density. The red arrow shows the accepted value of about 0.00729. Intrinsic proton spin derivation. This is one of several papers that derived the measured value of Planck's constant H from analysis of quanta spinning in the proton bit cycle. Here is the proton bit cycle showing that it can move around. Light speed derivation. We can fire one state quanta into a simulation using the binary mechanics lab simulator and measure the speed of light by noting the arrival time of these quanta to the other side of the simulation. If we have a cubic volume that we're simulating and we shoot quanta in for a light signal on one side, we can see how many ticks of the binary mechanics lab simulator are required before these quanta arrive at the other side. That's what this unidirectional light speed measurement data is showing. Here are the details of how all of that was calculated. The calculated light speed, of course, is bit velocity v divided by pi, so that we can express light velocity in bit velocity units of 1 over pi. In those units, light front velocity was approximately 0.319, or within about 0.3% of 1 divided by pi in bit velocity units. This is a remarkable result. Elementary charge derivation. We can take a look at what happens with the electrostatic force in the scalar bit operation. If two like-signed charge, these are the M-type quanta shown by circles, if one moves this distance, the separation then is the hypotenuse, and we can calculate what the electrostatic force actually is, and therefore determine, using Coulomb's equation, what the value of the elementary electric charge is. Intrinsic electron magnetic moment derivation. Our calculations give you the measured value in joules divided by Tesla units for the Bohr magneton. So finally, unexplained measurements are now all accounted for. We've done a great job. We have beat the big boss in the game of deriving primary and secondary constants. The basic result is that the primary constants of binary mechanics shown in the green full quantization area here of our open world have won the game of physics. Have a great day, you all.
Jim, I just put up one question there which occurred. It's a fairly basic one, and I mean, your whole thesis, I suppose, really is based on answering this. But Quest put this question up. I don't know if a one-liner can be obtained, but what proof is there that time and space exists as discrete units? Now, I know you're using this as a hypothesis, but I mean, suppose you had a quick one-liner like that. would you have a very quick answer to Quest as to why it is superior to take time and space rather than other quantities like energy as discrete rather than continuous entities?
Well, the in science we really don't have proofs. What we have is an aggregation of evidence. The contrary theory is that of continuous space time, which has been prevalent in science for millennia. And the new approach is the quantization of space and time and energy for that matter as well. So that where do we find the preponderance of evidence pointing one way or favoring one way or another? Remember, the objective is not to prove anything. The objective is to better understand our world. In the case of the outdated, in my opinion, theory of space and time being continuous, we have the total failure over decades to derive the so-called fundamental constants, which are the greatest body of perhaps unexplained phenomena in physics. So that the record of the theory that space and time is continuous is one of complete failure over well over a century. So physicists had a chance and they blew it because the chance was to try some alternative. And the successes of binary mechanics are adding up to favor the understanding rendered by quantization, what I call full quantization of space, time, and energy. So that's my response to the question of where's the proof.
Okay, well, we can perhaps come back to that in the discussion later because I think Quest is putting a further question in about that. Shall I just disappear and give you the stage again, or do you wish to come back with that second video, maybe now or later, Jim?
Well, I could proceed with the second video. Let me ask, when the apparent transmission of the first video was sort of halted or disappeared from the screen, was the audio still heard or was the audio also missed?
Well, I didn't quite experience that. I did experience some further breaking up of the audio, but I didn't see the presentation disappearing as such. I'm a bit surprised about that.
So that may have been just in my feed. Okay, well, let's then proceed with the second video. And I would introduce this by saying that the first video dealt with two uses of math in binary mechanics investigations. The up and down arrows shown in the previous video, where we tried to use the measured values of the so-called fundamental constants to determine what the primary constant values are. And you notice those are not the Planck limits, which are complete fictions, because those Planck limits are merely further unexplained values because they're based upon the unexplained values of light speed, the gravitational constant, and so forth.
Okay, so I was about to say that
So
perhaps we leave the showing in your hands, and there's a bit of a delay,
video.
by the way. I think
in the
our
second
live.
video, we're going to. In the second video, we're. Yeah. Okay.
Jim, we're getting
in the second video, we're going to look at how
major audio problems again. I'm sorry. There's a delay, and you're speaking and I'm speaking. So perhaps I'd better show the second video. What do you think?
Yeah, maybe that would work better. It's called binary mechanics equations.
However, how would you get that video to me? it's too big to email. So I think this is going to be a bit problematic.
In my email to you, I gave both a BitChute and a Rumble link to it. So if you look at your email, BitChute or Rumble for that video.
Is this an email you sent to me recently?
Well, it would be several days ago, I guess.
Okay. I can search for that in a moment, but I have sort of on second thoughts. I'm proposing maybe that you get rid of your video, because when we speak now, you're breaking up. It's just got pretty bad. So why don't you delete your video? Just get rid of your video, keep your sound on, and maybe try to show the second video, and we'll see does that solve the problem. Because just ordinary conversation is too bad to proceed. It's what we had at one of the conferences some time ago. So can you make your video stop cam?
Well, okay, in the private chat. In the private chat, Ian, I put the links to the same video. There's two links. You can use either one to show that one if you want, sir.
Okay. Well, I'll show it then. But did you get my other point? Your ordinary audio is breaking up when we speak now at this very moment. So I'm suggesting that you stop your camera. Maybe when you come back. Okay. Oh, okay, you've done that. Okay. Well, I'll try to show your video now. So just give me a moment. I'll try those two links. Thank you for them. Okay, let me see now. Okay, so all I have to do is try to share my screen now. I have this up. Okay, I've got an advertisement there. Sorry about this.
Instead of dragging their paws, they're bouncing around like they've discovered the world's biggest squirrel convention. All about your dog's gut health. By introducing some friendly bacteria into your pup's tummy.
I'm not sure what that is.
You're basically giving them a turbo boost.
Maybe that's an ad
that could power a small city. A coat so shiny you might need sunglasses.
Check out our new chat feature for live streams. Support creators with chat bombs. Try now.
Understand a little bit more.
Now you can make it full screen.
I'm stopping. Yeah. Okay. I'm stopping it there just for a moment, just to check that everything is working. So you can hear it, but you want me to make it full screen
in the video.
Okay.
Sure.
Well, I'll go back and I'll start. And I'll try to. Let me see.
More about binary mechanics by looking at its equations. The only mathematics that you need, a 3 or 4 year old child already knows, because these three math ideas are built into language, understanding and speaking language. The first of these three ideas is full or empty. The truth table for and logic is shown below. Is it true that Jack and Jill went up the hill? If the little boy who went up the hill is true, the output is 1, that both Jack and Jill went up the hill. Any other combination is not true. The third idea is not logic. In the failed standard model formulations, which at best can only approximate physical events and which look like this. Yuck. Could you tell the roosters to stop making all that noise? What? Forget it. In binary mechanics of the spot unit, where we have two kinds of energy, M and L, shown by circles and arrows in our diagrams, and energy is quantized because M can equal 0 or 1, and the L can equal 0 or 1. In quantum in the X direction, the Y direction, and the Z direction. If we fool around and change the direction of the arrows, like shown in the lower left here, change the sign of the one states, which we call the M bits, and things like that, we get finally a spot. And our model states that is a lattice of these spot cubes. For any theory of everything in physics, you only need things. The system state definition, that's what do we have? And secondly, it's time development, how it changes as time marches on. So now let's do like a walkthrough of the basic equations of binary mechanics. Equation 1, which is actually two equations which we saw on the last slide. M equals 0 or 1, and L equals 0 or 1. Now that was the spot unit. We combined through 0 of the three M loci, and the three, we have what's called the bit function, which replaces the antiquated, outdated 20th century, the bit function of spots. It just depends upon how big your computer is, how much computing power you have. What we need to do is at the US National Labs and CERN over there in Europe, and use those computers, say, to model the cesium-133 atom, which is a clock, and see frame by frame exactly how it works. That's the new technology that mechanics brings. S sub I in three spatial dimensions as a spatial frame, and yes, it has integer of any position in this space by this formula, and that parity is going to equal 0 or 1, even or odd. And so for each dimension, S1, S2, and S3, so X, Y, and Z are even or odd. Next, let's consider the X, Y, and Z dimensions in our space S as a cyclic ordered set, or what we call chirality. We're going to let the I and K represent the three parities of each spot unit oriented equations here, which describe this chirality and maps X, Y, and Z to I, J, and K. Using this information, we can then define the charge for and its color charge and the direction of the L loci. Does it point to the right or to the left? So we take a function that we're going to call sine of the m loci, and we're going to raise -1 to the power of the -1 for, say, electric charge. And we know from simple algebra that if we raise any number to the 0 power, it equals 1, or it's -1. We can get with this sine function a property of m loci depending upon -1. Likewise, we can do the same for the L loci in equation 6 here by raising -1 again, but this time to the power of the k parity, which gives you the direction +1 or -1. And we just establish a convention that +1 is going to be right or left and -1 is going to be the other direction. And we go along our jolly way, and we've now defined our system.
Hello.
There's a simple brainwave method that can rev up your brain power and help you easily manage.
Now, that wasn't too tough, was it? That was pretty good, I think. And that's 1/2 of everything you need for a theory of everything. Just by the system state, we get a whole lot of results. Let's look at this table. Here's our bit function for the x, y, and z dimensions of our space. There are the 8 types of spots, which are the modulo 2 parities of each of these spot units. Each of these spots corresponds to an elementary particle, shown down here in the lower left. We have the arrow pointing to the left or to the right for minus and plus L from our sine functions. And the same way with the m bit being plus or minus, with the plus likely represent the spot units. And the different permutations of them actually predict h is less than the ridiculous number of elementary particles that you see in many publications about the standard model physics. Actually, all those other particles are combinations of these fundamental 8 particles here. Find pairs where m or L equals 0 or 1, and these 0 or 1 states can be shown to have a unique configuration elementary particle. For example, when the m is -1, we have a lepton known as the electron. If all 3 m's are positive, we have the right-handed electron known as the positron in the lepton category. Here for reference is the signed complex version of what we showed above, just for you guys that love complex numbers. So what are the properties that we can derive or discover from the simple system state model that we presented? A whole boatload of stuff. For example, the charge Q is the sum of our sine m sub I values divided by 3. So we get the charge of the electron as -1. Next, we can get the handedness, right or left, by multiplying the 3 L sub I quantities together, and that equals h. The handage is right or left for that particular elementary particle. And we see here that if all 3 L's are minus, we're going to have -1 times -1 times -1 equals 1. That might be on the test, so you might want to write that down in your notes. Multiply them together, 1 times 1 times 1 equals what? We're waiting. Handedness for the electron is +1. Now, for these three d or down quarks, they're all right-handed, +1, as shown down below. And we have the three colors, red, green, and blue. And by the way, those colors also depend upon the M locus sign function another day. But the three colors are predicted. The same way for the three antimatter quarks, blue, green, and red, which are left-handed. In the appendix of my paper, Binary Mechanics Postulates, we also, a lot of particle physicists talk about three colors, but there's four. The four colors, red, green, and blue, are shown correctly here for both the antimatter and the matter particles. And the fourth color is no color, 0, for the leptons, the electron, and on the left here, the positron. So our four colors are also predicted simply by the location and orientation in the X, Y, or Z directions of our spot units. This is a remarkable set of results from such a simple 6 equations of the system state of binary mechanics. By the way, I say 6 equations, but you could say there's more because equation 1 is really 2 equations, and there was all the chirality mapping that we did down there. And so the point is that all of the information is there. So however you want to list it, it's very important that all the information is there, because in order to write it, you have to have exact information inputs. It can't be, well, it could be this, or it could be that, or maybe it's the cat's dead or the cat's alive. You have to know exactly what's going on in order to even write a computer program to do that, to do the simulations in the free download of the Binary Mechanics Lab software. So if you like to tinker around, get that software, okay? Now let's look at the rest of the story. I said all we needed was the system state. We did it. Now let's do the time development, which is the bit function change over time. We have 4 bit operations, which are analogical to the operators in 20th century operations defined. And that's all we need to make our universe. Along with applying these operations in a particular order. When we quantize everything, the infinitesimal increments used in the old-fashioned 20th century quantum mechanics are not applicable anymore. Everything is quantized. So what antiquated quantum mechanics called operators are called bit operations in binary mechanics. With reference to the relativistic Dirac equation, we had to move into our quantized world and represent momentum in the unconditional bit operation, which is really simple. It's simply the state of the M loci becomes the state of the L loci. So what happens to the M loci, which is L sub x here? So that the state of that carry bit, L sub x, becomes the state of the M loci in our spot unit. In this diagram, we show in one dimension the unconditional equal. And notice that at time equals 1, the M and L quanta shift in the L direction. The L direction in this example is to the right, so that this 1 goes to there, this 0 goes to there. That's why it's called unconditional, because it just happens. The scalar or electrostatic bit operation. First, we can define the state of the locus M sub j. In this diagram, we can define two types of arrangement of spot units, scalar bit operation, where our potential is mj, which is right next to the quanta that will move to the L position if mj is in the weight. Now the product or and function of E phi is a Lorentz force component and is simply and function or the product. You notice those are the same, going to equal 0 or 1. So now we can define the scalar force, which is the and function of the source loci M, the adjacent concurrent loci, M subworld could that be? That's not L. It means that loci in the same spot unit as the source is empty, so it can receive a one state moving into it. This last 1 minus L component, 3-item and function for the scalar force, is required because, as we've said, locus can only contain one quanta at a time. If it could contain more than that, then we wouldn't have really reduced things down to a spatial cube locus can only contain one state, the 0 state. So if the scalar force F is 1, then the 1 state in the M locus is moved to the locus at time equals 1. The vector bit operation is quite similar to the scalar bit operation. In this case, we take the Lorentz force component in one dimension, which is shown here as L sub cat is our magnetic field. So this illustration shows the M source and the potential L sub k in the countercurrent location, right next to the source one state quanta. And there are different permutations of that situation shown here. We now have the vector force is the product of your source, the L sub k vector potential component, and an empty destination L type loci. The scalar and vector bit operations are shown in examples here. At time equals 0, the input sample data, the one-dimensional component of the vector potential A from the Lorentz equation. And you can see that you're going to move the source one state to a destination L-type locus here. And the same thing occurs in the example shown for the binary mechanics, a sort of field theory. Well, yes, we have defined that all of the M loci are the electric field. Not all elemental volumes of space have an electric field. Only those that have one state, and because we don't need an infinite number of points in any arbitrary spatial volume. All we need is our elemental volumes defined by the primary length constant in binary mechanics. Kinds of fields, according to the basic equations, the distribution of the A vector component is the magnetic field. And by the way, it seems that these are also the long sought after magnetic monopoles. Eureka! Everything in the first 3 bit operations occur in one dimension, so that when we are, it doesn't matter which spatial dimension, X, Y, or Z, we compute first, because what occurs in the other dimensions. So we can do them one at a time to get the new state of our world. The strong bit operation is different, however. It deals with the transfer of one state within a spot. We call that intraspot. So the strong force has a source one state in one spot unit. Its potential is actually a neutrino, which is the other locus in that source spot unit. This is really weird, isn't it? And of course, the same thing as we had before, a empty destination locus. And when all three of those things are true, then the strong F equals 1, and we get a transfer from the source spot unit of a quanta to the destination spot unit. Is disabled by what we call inertia. We define inertia, P, as the product or and function of the M and L loci in a spot unit, and that can equal 0 or 1. In this case, it equals 0 because the black arrow shown here at time equals 0 is in the one state, and the empty equal here is our M locus in the 0 state. If P equals 0, the L type equals 0 moves to the Y spot unit in the M type quanta position at time equals 1, as shown here. If inertia P here at time equals 0, at time equals 0, the L quanta does not move from the X spot unit to no change here. In that case, in the next unconditional bit operation, what's going to happen? This one state quanta here will shift out to the next. That is the. So now we have the mechanism of motion, where one scalar elementary particle location, that's what a spot is, to another spot, two ways, by the unconditional bit operation or when the strong force, as shown in the lower part of this diagram. Now with chirality, in other words, the right-handed and left-handed nature of our 8 elementary stations, intraspot transfer of a one state that I've been talking about can either go one way or the other, so that the D here in the destination, which must be empty, is computed with equation 16 to be equal to N or P for the left or right spots. In other words, the direction of the shift between one dimension and another in the strong force depends upon that simple. Finally, is the question of bit operation order. How do we run our universe? It's like a looping computer program. And in this case, what equation 17 says, that the bit function, in other words, the system state, at time equals 0, and the unconditional bit operation, in this case, the strong bit operation, so that at 4 ticks of our primary constant time, we have a new system state, a new world. And that is how simple a theory thing differences between the scalar or electrostatic bit operation and the vector bit operation on the right. The electrostatic bit operation occurs only between spot cubes. Slide before. you can see that the only way to get concurrent pointing in the same direction spot units is between spot cubes. They don't occur within a spot cube. On the other hand, all of the magnetic bit operations occur with countercurrent spot units. Countercurrent means they point in different directions within a spot cube. A similarity, as we've seen, is that when everything is true for the M bits, from the M to the L bit loci. So you're probably asking, when do we get to the hard part? Well, actually, there is no hard part. The way the universe works is very simple, as we've presented here today. Theoretical physicists need to be very practical. You can't have like 10 or 11 equations. Every little thing that wasn't taken into account before is another term added to an equation which nobody understands. That just doesn't work. That's not parsimony. That's not Occam's razor. That's not practical. If you call up a supplier and shut up. If you call up a supplier to order an infinite number of a huge number of supercomputers that are, and since sum all that up and compute what the value of that field is, instantaneously, the supplier is probably going to tell you, have infinitely small computers. We don't do Miracle Guru or whoever, because you're talking about something which is sort of magic. And the 4 binary mechanics bit operations with a conventional force classification, which is based upon particle interactions, which is obsolete way to proceed. First, the so-called electromagnetic force is actually maps to 2 different bit operations in binary mechanics. Second, the so-called strong force involved in the structure of the proton maps to a force in binary mechanics. But the use of the word strong can be confusing here because it has a different meaning in the conventional and the binary mechanics approach. And that can be confusing to people, I suppose. But these are just words. The important thing is what the equations say. Now, the so-called weak force and neutral weak force involve the so-called plus or minus W bosons and the Z boson, crazy stuff like that, which we've shown here at Binary Mechanics Lab that the unconditional bit operation alone produces these particle interactions. So the W and Z bosons are identified as related to the right-handed matter d quarks. And by the way, there's some experimental evidence that if you look at the statement I'm making is actually probably the best way to interpret that data. Whatever the theories that the experimentalists have when they gather their data, it doesn't matter. Maybe they're asking the wrong questions. You can look at their data and ask different to a better conclusion, which is more relevant. Lastly, gravity is not a primary force. Thus, quantum gravitation unification is achieved in binary mechanics. Actions of 4 of the bit operations produce the gravitational phenomena. And thus, quantum gravitation unification is achieved in mechanics. Now, if we march along and transition from legacy physics in the 20th century, and for many people up to the present, to century physics, in our summary table below here, unconditional bit operation does not define a force. The so-called weak force is due to the unconditional bit operation. That's how lost many contemporary particle physicists are. And we see that we have three forces defined: scalar, vector, and strong. Each of these three forces, source, one state, locus, and adjacent locus that has the potential for that force, and a destination state locus to receive the incoming quantum. In the bit 6 and its time development, the rest of the equations are complete and correct. Suffices to represent fully any known physical system and its dynamics over time. Any exception would imply that the postulates are incomplete or incorrect to some extent. We just talked about figure 5, which cross-tabulated the conventional classification of physical forces with the binary mechanics bit operations, highlighting several key advances. First, in vector. Second, the unconditional and strong bit operations entirely account for color confinement. That's the circling of bits in the bit cycles, and other videos explain all of that. The unconditional bit operation produces so-called weak interactions, which therefore do not qualify as evidence for a fundamental force. In summary, what particle physicists have been doing, and in most cases getting no, is use of supposed particle interactions to define fundamental forces, which has clear, consistent results and lacks scientific merit. In other words, say for gravity, which is not even a force, and yet they're going to say there's to join us and play the game. Take care, be happy and healthy.
Okay, we'll we'll endeavour to. Well, first of all, I'll stop this. I think we're probably back now. Yeah, thank you. Actually, if I may say so, I thought that was a fascinating video, really remarkable. I thought that would just be an add-on. That's really remarkable. It was actually admittedly very turgid, but the beauty of it is that it's available now for all time for people to go back and look at it, and maybe to explain to colleagues who don't know what this is all about. So thank you very much for that. And it seems quite remarkable that, you know, the way you've looked at it is it's like a very interesting symmetrical sort of formulation. And maybe you know, some of the sort of like design people would say, well, the universe was created by a logician, because you know that's the way you've extrapolated the binary mechanics lab simulator and looking at these phenomena and these equations into how the universe operates as a whole. However, I suppose if you're finished for the moment, Jim, unless you want to say anything more before we get to the questions.
Well, I probably said too much already, so I'll get to the questions.
Okay, and my apologies now, because I'll have to strain your patience for a few minutes. I had my full attention to this and it was full screen, so I haven't seen what's been coming in the last 20 minutes. So if you just give me a moment, I'll scan through them just to see. We just have normally people like Quest and Cerna Hepta making most of the comments. But if there's any specific question, I'll try to deal with it. Luckily, you've been able to see this as well. But
the first question of Quest was very important about proof.
yeah,
It's very important for people to understand in science. We're trying to understand things better that may have practical results. Um, it's not a matter of proving something, as in, for example, a court of law or whatever, So this idea of prove me this or prove me that, as soon as that issue is brought up, you're not talking with a scientist anymore.
you could possibly disprove something, couldn't you? I mean, if you have some system and there is some experimental evidence which flies in the face of that, well, that would
Yes,
disprove.
thank you for that clarification. We call that eliminate. For example, my own work and many studies which you yourself, Ian, have referred to, have eliminated general relativity. As I mean, if you're going to treat general relativity and binary mechanics on the same footing, we have things that eliminate general relativity. As far as I know, no one has succeeded in eliminating, providing some evidence that eliminates binary mechanics postulates.
And actually,
That's
to be
a crucial difference.
fair to you, you on a number of occasions have tried your utmost to do that, because that's a very
Exactly.
a very advantageous thing to look at your own theory in the most critical way and actually try to disprove it. Okay.
Like, for example, I created electric fields and showed that protons and electrons move in opposite directions exactly as would be predicted. Then I, in another effort to sort of disprove or eliminate binary mechanics, I created magnetic fields in the simulation and showed that both protons and protons and electrons were pushed in the same direction with the magnetic field pointing one way or the other. And so that again was, a failure to eliminate binary mechanics. Everything I've tried seems to just work.
Cornelis just has a quick question. How can there be attraction in a discontinuous space and time? Answer that quickly, maybe.
Very good question, Cornelis. Applause to you, sir. If you look at the binary mechanics equations, after you sleep it off and wake up the next morning, maybe with a hangover, and if you look at them, you say there is no attraction in binary mechanics, period. The equations show repulsion of like charges in the scalar bit operation. There is no equation for attraction of opposite charges. But what happens? I tried to look at this by tracking proton and electron movement. And it's the paper, I think, is called, that in that paper, I tracked the motion of protons and found that the electrons tend to follow the protons as if they were attracted to the as if the opposite charges were attracting each other, even though in the equations running the simulator, there is no equation for attraction. There's only the equation for repulsion. So you could ask, why do the electrons follow the protons? Well, it could be that the protons is the direction, the center of gravity, you might say, to use a physics term, of the protons contains less electrons in that direction. And so that's the way so the electrons are actually being repulsed by other electrons away from the protons. And what you then actually see in the world is that the electrons follow the protons. Are you confused yet, or did I answer the question?
Well, we might bring Cornelis in a moment because he is in the green room, so perhaps he wants to say something more about that. There's something from.
Well, he always has good questions.
Yeah, indeed. Yeah. Okay. We'll try to get through these pretty quickly because we leave a little time for the discussion.
Yeah, in a way, since 2010, there's some 100 papers published in the Journal of Binary Mechanics, my website there. Almost all of those studies have been framed to see if what is predicted actually occurs, or if it doesn't, then we've eliminated binary mechanics or found at least some fundamental error in its formulation, if not completely eliminated it. And that has always failed. Binary mechanics has always just beat the hell out of me. Anything I try to
look at this, what I've called a sort of a symmetrical system, and it looks most elegant, but they may, at a first glance, say, well, look, you're looking at your dimensional analysis and you have MLT in there and everything is expressed in terms of that. But why don't you have a Q as well? I mean, we normally talk about, mass, length, time, and charge.
Well, the sign of the M in that equation is the charge, sir. And it's 1/3. It's called the fractional charge. And I call it the elemental charge in my constant derivation tree diagram, because the word fractional charge, if you look closely in the physics literature, is used in slightly different ways by different authors. And so I'm okay with calling it fractional charge, but to avoid confusion, I just call it elemental charge, which is 1/3 of the electron charge. Does that address what you were saying?
Yeah, no, this is, I mean, you consider mass and energy anyway interchangeable, I suppose. And this is similar to the idea of the quark, the charge of a quark, I presume.
Yeah, you have the 1/3 charge of the six fundamental particles of the quarks, the antimatter and the matter ones. And you just mentioned something very important. You said interchange of the two types of energy, M and L. Well, that occurs in the unconditional bit operation all the time. And you might call that a resonance between the two types of energy. This is a whole area that requires a lot of exploration. But as long as as long as theoretical physicists are hung up with antiquated 20th century quantum mechanic formulations based on the theory that space and time are continuous, they're going to miss out on the party. There's all kinds of stuff to explore here, which are, the victories of tomorrow, like just the unconditional, what you just said about the exchange of the two types of energy, M and L, occurring. Well, that's a resonance that's occurring all the time, which is a very important thing.
You see, in our community, of thinkers and mainly alternative thinkers, I often think that there's a lot to be gained by sort of integrating aspects. I mean, you've had certain insights, and maybe other people have had certain insights. I'd like to think I have certain insights, and we could maybe integrate some of those things to get a fuller picture. But if I may be a little critical of all of us, including myself, we tend to have our own way of looking at things, and there may be divergence when we get something like binary mechanics, or something like my ideas or other people's ideas, Cornelis' ideas. We react a bit because they're not consonant with our own ways of formulating things, and we can be our own worst enemies in a way by we attack. The outside people see us attacking each other very strongly instead of maybe saying, well, is there something in that I could maybe integrate with some of my own ideas. So perhaps we should take into account the words of Benjamin Franklin when he said we should all hang together, or most assuredly we should all hang separately. We tend to be rather critical of each other. Anyway, just a comment. Okay. Well, let's see, because the time is pushing on. If there are any more questions which come in, I'll try to keep an eye on them. There is correspondence between Watteo and Cornelis and so on about waves and particles and so on. I might bring Cornelis in if he's there, because he's made a couple of other points which I didn't put up specifically. He's muted and there's no camera, so maybe he's not there. And we can have a okay while he's looking at that. He seemed to be posting some questions, but he doesn't need to be there. Is Carl Reef? Is he there? He's not muted, but he's no camera. He's in the green room. Okay. We don't seem to have many people. We had a comment from Harry earlier, but I don't think he's joined the green room. So perhaps we'll, in the absence of anybody coming in directly, we'll just maybe have a little more conversation, which I was skipping through quickly, about
well, you were mentioning, Ian, about how the work of different critical thinkers in our CNPS sphere here actually can complement each other. For example,
yes.
There's nothing in my full quantization approach which eliminates wave analysis. You can look at the bit function and start to sum up all of the quanta over a particular extent of space and time, and treat those as waves and analyze what's going on at that level. That's not a contradiction. That's just another, in other words, binary mechanics does not exclude a sort of proxy assumption of continuous space-time, as might be done in looking at the bit function changes over time as a spatial temporal pattern of waves.
Okay, well, perhaps while we're just, I see a number of comments coming in, but something that really occurs to me, and I think some other people may have some questions on it, because you have adverted to it over a considerable amount of time, and you reminded us of this recently, but maybe we're a little unclear. You've given us references, but what I'm talking about, Jim, is you have, this binary mechanics simulator, and you have software which you've developed, and it's available at present, I understand, for people to download themselves and to do some experiments. Could you say something about how one might access this, and how it might be used for a person for whom who's coming to this, for the first time, for whom it's fairly new? Should
Well,
they go to the website?
I've done an analysis just in the last 2 days of cooling down a system starting at 5/8 of total energy density. In other words, 0.625 energy, which is sort of the borderline between our formation of high atomic number atoms and the breaking up of those atoms into a plasma form in the analysis of binary mechanics. And what I was looking at was the quanta leaving the simulated space as it cooled down. And I'm finding that I can detect individual particles of both protons and electrons, and maybe over the 3 generations of those particles, where by looking at the actual number of quanta leaving in each of the 6 faces of the simulated volume, and correlating those exit events with the change in the charge. For example, when when you have a number of quanta leaving at a particular point in time, you can look at what change in the total charge occurred? Was it if the total charge is more positive after the particle leaves, that must have been an electron or a negatively charged particle leaving. And so what we're getting at here is a possible way to start reverse engineering a number of things, including the measure of pressure called in pascals. And so, because I'd like to be able to say at a certain energy density, we have so much pressure in pascals. We haven't been able to do that yet. So there's dozens of questions like this that the binary mechanics lab simulator can be used to explore. Over the history of the simulator, I might add, new features were added to enable addressing new questions or new hypotheses that come up, so that the current state of the binary mechanics simulator is basically represents the evolution, the features that it now has represents the evolution of what questions we were trying to ask, what hypotheses we wanted to test. So let's say someone looks at binary mechanics, the equations that been presented and so forth, and looks at the simulator and tinkers with it a little bit and says, hey, I'd like to do this experiment, but I don't know how the simulator in its present form could do that experiment. It could be that I could then explain to the person, maybe by an email exchange or whatever, how the simulator could in fact be set up to do that experiment and to test that hypothesis. Or say, my goodness, this is a wonderful question to ask, and I think I'm going to have to update the simulator, add new features to it so that we can then address that question.
You've in our earlier private conversation, you've very kindly offered to give us more information and talk to us again on some of these aspects. I'm just wondering if it wouldn't be useful to people if you gave us some talk in the future, or some demonstration at least, maybe by video or real time, about downloading the simulator and doing one of these experiments, the sort of extraneous experiments just on pressure or God knows what, to see how it's actually done and what the results are. Do you think that might be possible?
Okay, well, that's a good idea, because there's so many different experiments that have been done. As far as the videos on BitChute, YouTube, and Rumble, they're all the same videos. So you could take your choice as to where you like to look at them. The oldest site is BitChute, and so that it has the most views, if that sort of thing is of interest. But I might emphasize, in science, we don't take a vote as to what's the correct idea. We have to just start to think for ourselves, which is what we do here at CNPS. But there are already, I think, 3 or possibly 4 or 5 videos or papers about use of the simulator and what you can do with it, to introduce people. And there definitely could be more, as Ian has suggested.
So this is on the BitTube or whatever, BitChute.
Yeah, I think there's 3 videos: how to get started, and a quick start using the simulator, where you just use some default parameters and don't have to do much of anything, but you can then see it run. Then there's a very important video showing the fact that the positron spot actually is the 3 spot units in it are parts of 3 different proton bit cycles in adjacent spot cubes. This is an extremely important result in nuclear physics, and I just published a paper about that whole question, about what's called the proton cycle network. And so that's on the binary mechanics blogspot.com site, as a recent paper, so there's those videos. And of course, I've actually presented other stuff here in CNPS a long time ago about inertial propulsion. And as I say, I have a new setup where I put in two gyros, much as the Boeing satellites do, to levitate them because they're in near Earth orbits, and otherwise they would fall to Earth. They're not high enough. But the levitation from the inertial propulsion provided by these two gyros um, keeps it up in the air. The satellite's up there. And so what I tried to do is to simulate that by creating two circulating regions next to each other and looking at which way things tend to move, and is there in fact a levitation or a movement in the predicted direction. And that seems to work out quite well. I haven't published those results yet, but they're all there for your consideration in the future.
And I mean, if you were willing and able to give us a short presentation on that, maybe in the coming weeks, even, as we discussed briefly.
Absolutely, yeah.
Because there have been a lot of emails and conversation on this. I don't know how many people have been party to this, but you probably have, Jim, yourself. People like S.I. Wells has been sending a lot of information over the emails about his own ideas. And of course, Dennis Allen also has done some work on this with some of his colleagues. And people are talking about the late Eric Lathwaite and so on. So it's sort of in the ether, if I may use that expression.
Well, Dennis Allen was the one who pointed me in the direction of looking at inertial propulsion in the first place. Okay. So that your statement that among us sharing ideas can have a beneficial result and be mutually helpful to everybody. Yeah. So that's thanks to Dennis. Shout out to Dennis.
Indeed, I might even echo that ceteris paribus, some of my ideas which I've been presenting on, and I will be giving a Saturday talk maybe the end of next month, but many of those were sparked actually by Dennis Allen, because he referred me to the work of Wesley and other physicists and his own analysis, and that got me thinking further about some of the preliminary work I had done. So it's all cross-fertilization, there's no doubt about that. May I just ask one thing, just while we're waiting for the questions as well? I mean, some people may be interested, Jim, in how you yourself first got the idea to look at the binary mechanics, or to develop the germ of the idea, which then led further.
Okay, this takes us back to, let's see, it was about 1993 when I lived in New Jersey. And a fellow who was named James S. Hughes, and he cited in my paper on binary mechanics, and also the more recent paper, summing up things in a more user-friendly way, perhaps, binary mechanics postulates. He had this theory that that actually the spinor matrices in a pair of relativistic Dirac equations of opposite-handedness actually define the points of a cube, the vertices of a cube, the 8 vertices of a cube. And on my blackboard in my kitchen, you see, we nerds, we tend to have blackboards in our kitchen. And I guess today we would have whiteboards, but in that day it was actually a green board, I guess you'd say. And so with some chalk and everything, he knew I had a lot of experience in programming matrix algebra, advanced statistical programs, and computing eigenvalues and vectors and rotating matrices and things like that. So he wanted to show off his theory. So he showed me how he could rotate the 8x8 spinor matrix of a pair of Dirac equations of opposite handedness produces, and get the vertices of a cube. In other words, all the imaginary values in the original spinor matrices that any of us who has looked at anything in quantum mechanics, you see all these imaginary values there, they disappeared into real numbers showing the vertices of a cube. And so he claimed that space was actually a lattice of these cubes. And Hughes, I lost contact with Hughes because he went off to Africa, and I think I went up to Alaska for a period of time. At any rate, Hughes actually planted the seed in my mind, because I said to myself, if Hughes is right, this is very, very important. And I asked myself, well, what is the size of these cubes? You know, I mean, there has to be a size, right? I mean, if you're saying that space is a lattice of these cubes, you know, it's obvious that, you know, any idiot's going to ask, well, what size are they? So I started there, and I just said, let's go full quantization. Let's not only quantize length, which would be an indicator of the size of Hughes's cubes, but also energy in terms of mass and time. In other words, the units of measurement in physics. And let's quantize all of those and go from there. So to answer your question, the germ of it was from this amazing man, James S. Hughes, which, by the way, was a former MIT student. Very bright guy.
Okay, well that gives further credence to the proposition that, you know, we're all bringing different ideas based on our own experience and promptings by various individuals to the whole subject, and we should really value that and celebrate it and try to, you know, integrate these little bits of insight.
Yes, I have papers
opposing.
I have papers that James Hughes wrote, and he was circulating those around various universities and things before I lost contact with him. I don't know what happened after that. He went to Africa, I was told. But at any rate, I have those original papers, which are probably of historic interest. But that was a major thing that this guy did. And so that was right in my kitchen in Medford Lakes, New Jersey.
Right, literally as well as metaphorically in your kitchen with the blackboard. Okay, well, Cornelis, I can see you in the green room, although you're muted, and you've made a number of points here. I referred to one of them. But, if you'd like to come in and maybe just, you know, mention some of the points you put into the chat. I know you were chatting a bit to Quest and to this other person, Watt Teo, I think, about waves and repulsion and so on. But or have you any general response to what James has been talking about today and the mathematics and how it's all apparently coming together to explain the universe? You know, you're mute, Cornelis. Can't hear you. You're mute. You'll have to unmute yourself. That's odd. I don't know why it's causing a problem. I
can't hear you.
Yeah, he's
muted.
He's yeah. The guest has to unmute himself.
That's what we might call self-censorship.
The StreamYard said the guest has to unmute themselves. They want to be politically correct. I say the guest has to unmute himself. Singular pronoun. Anyway, no, if you can't unmute yourself, Cornelis, we're going to have to leave it.
Apparently, he can't hear us.
No, he can't hear us. That's very odd. He must have no sound. No, he can't hear us. Okay. I don't know. He seems to be responding in a way, but I'll have to remove him. Okay, that's unfortunate. Because there were one or two points in his discussion about, I don't know, they were talking about ether particles would have to repel each other. I don't know what they were getting at. And how do you explain that or something?
Well, that's the scalar force, the scalar bit operation, the repulsion of like charges.
It could be that. I'm saying that ether theory requires the underlying particles to have repulsion properties. There is no repulsion, just attraction, because you'd have like elements. I mean, to me, it's like a micro.
Well, in binary mechanics, the scalar.
Yeah. I mean, what does binary mechanics?
In binary mechanics, the scalar bit operation deals with repulsion, and as far as the ether goes, the actual total energy field, which is the sum of the electric and magnetic. So in a way, binary mechanics defines the ether as a combination of spatial structures as well as their content, which are the one states. Taken together, they define an absolute reference frame, in fact, known as the ether. By the way, people are talking about relative velocities and accelerations and special relativity, for example. But without the absolute frame, you have no idea. There's no way to know if anything is even moving. And so that's a great way for physicists to avoid the question of what is the mechanism of motion, because they have no way to know whether anything is moving at all anyway. For example, back to Newtonian physics, if you're in the frame of the object, it's stationary, it's not moving. And if you're in another frame, the object is moving at a certain velocity. Okay, but you don't know what its absolute velocity is because you need the absolute frame for that. And so as long as physicists can tinker around and avoid the fundamental real questions in science, then they don't have to really think too much.
So I see Cornelis may be coming back, but just one question on that before coming to that, because I'm certainly in sympathy with those statements. But I just question: do you conceive of a sort of a universal ether, or maybe a series of local ethers, such as
Well, I'll go with the universal. But I won't exclude the local either. What is the universal? As I just said, but to summarize, in binary mechanics, it's a combination of the idea that there is some structure to space, and then we add content to it, which are the one states or the zero states. Now, if you want to talk about local ether, you could say, hey, Jim, let's just analyze a certain section of our bit function in this area and see what's going on there. And maybe we could then say, we're talking about what's going on with the ether locally in a certain area, and that may have merit. But again, these terms that we're using are only words. The real definition of things is the mathematical equations. As long as we've got those, we can pin things down. But if we try to play only with words, as some prefer to do, because they really don't understand what the words mean anyway of what they're saying, then there's just really probably no end to confusion and lack of communication and misunderstandings among different people. But if we deal with the math and the simple binary math that I presented and the equations, well, any particular one of them is either right or wrong. Yeah. And we can focus on.
They don't rule out or in. They don't rule.
Excuse me?
Any. Yeah. Okay. we just have a time maybe if Cornelis is available to bring him in briefly because we're running out of time. So we'll just try once more because he's unmuted now. Can you hear us, Cornelis? No, he's not responding. He's unmuted, but he's not responding. Okay, I'm surprised at that. His loudspeakers.
Maybe the speakers are off.
Yeah, must be that. I sent him a message, and Quest, who was corresponding with him, sent him a message as well. I think I can actually hear some background noise in his place, but he doesn't seem to be able to hear us. Well, you know, quite a number of questions have been raised from today's very interesting presentation, which, you know, we only had a brief possibility to discuss in maybe less than an hour. But what I'm...
Carl Reef has a comment in the private chat.
Does he? Because I tried to bring him in. What has he said? I didn't see it. Carl Reef. Is that some time ago? Oh, private chat. Very well. Hello, Ian. Can you send me your email? I can't seem to.
Can you send me your email address? I can't seem to be able.
Maybe we could figure it out during next week. You don't.
And he gives his email address.
Yeah, I'm quite. There's maybe a technical problem. I'm not quite sure what he means by that, but I can certainly. He doesn't want me necessarily to post my email address, just send him a message. Well, you've done it, yeah. Well, my email is not private. I'll put it in now.
But if he can enter something in the private chat, isn't he in the green room?
He is in the green room. I've tried to bring him in, but he's no video and he's mute. And when I tried to invite him, there was no response. But he is there. So I've just my email there. Maybe we could figure it out during the week. You don't need to post it here. Please just send it. Yeah, at Eigenwave. Interesting domain.
He says he can't respond for some reason.
Yeah, he's logged into the green room, but he can't respond. So I don't know. I don't know what I can do about that. Let's see, a couple of new comments, but Ian, I can hear you. Cornelis said, I can hear you inviting me, and I turned my mic on. My camera has always been on. He could hear us. I don't know. Try once more. Yeah. Are you there, Cornelis? You say you can hear me.
Can you hear me now?
Yes. There was a problem.
Yes.
Okay. Well, we have a few moments. If you'd like to be brief and summarize, we'd like your response as well as maybe any quick question. Were you talking about waves and repulsion and so on, or have you any other points you'd like to raise just before?
Oh my goodness, I got too many things going on here.
We've had very few people in the green room. In fact, you've been the only person live.
Okay.
Carl Reef has, but he couldn't get in either.
Is there a delay in my speaking, or is it okay?
Yeah, not really. There was a problem. We just couldn't get anything. But no, it seems all right now, Cornelius.
Well, I think that problem might have been mine. I have a cell phone that I use that actually talks through my hearing aids. And I was using that, and I was listening to the conversation, wasn't realizing when I was talking to you, I was looking at the computer too. So that may have been my issue.
That probably explains it.
Okay. Anyway, the thing that I look at with Jim's thing is he says there's only repulsion, or there's actually no connection, physical connection in Jim's system. It's all, this moves to here without an explanation of it moving from here to here, and it jumps. And he says there's no attraction. And in my understanding, I mean, intuitive to me, there can't be a wave motion without a bonding motion and attraction to cause a rebound. The only way you can have a wave otherwise
Well,
is
there's no
the material
attraction
you
in
have
the
has to be
equation.
contained in an enclosure, and it would be bouncing off the solid sides of the material. But otherwise, all you get is when you get particle pushing particle, you simply get dispersion. You won't get a return that you need to create a wave. And that's the way I look at it. So I think everything has to have a connection in order to have any kind of, there has to be a bond, all atomic material, everything that we see has a bond. Even the atmosphere, the air in the atmosphere is basically a wave. A sound wave occurs because there is attraction between all the molecules. They're condensed together because of the attraction and compressed, and then there's a compression and expansion. So to me, you can't create a wave that's needed to create anything unless you have a method of mechanical connection.
I think there might be a slight delay in the line between us, but did you get that, Jim?
Is everyone back? The equations of binary
everybody-
mechanics produce aggregation.
Aggregation.
So that should make Cornelius happy, because aggregation means things coming together in a smaller volume.
But what can cause the aggregation? There has to be an attraction for that to come together. Otherwise, you've got something from the outside world that's pulling it together. That's holding it together.
Well, the equations produce that result. So the answer to your question of what's causing that is the equations of binary mechanics.
Okay, but equations.
By the way, when you talk about things, go ahead. Sorry.
I'm saying equations
Excuse
is
me?
equations. It isn't a mechanical explanation for anything, a cause and effect explanation. It demonstrates, it simulates the action, but doesn't explain the action.
Well, well, in terms of the mechanical action, when a one-state quantum moves from one locus to another, that is you might call a mechanical event that occurs.
I would call it a miracle that it just moves from here to there. Just here it is, there it is. That's
It's like the
not
old
a
Zeno
mechanical event.
paradox. Yeah, the old Zeno paradox that you cannot move because you can either, to move, you have to move in the space you are or the space that you're not. Well, you can't move in the space that you are because you're there already, and you can't move in the space that you're not because you can't get there. So,
Yeah.
these are a bit philosophical, but yeah.
Well, in binary mechanics, you can get there. For example, both the scalar and vector grid operations.
Yeah, you can get anywhere you want to with a mathematical operation, but I'm looking at the physicality. How does this really interconnect? How do you move, and how do you get attraction, and that, and it's just it's mathematical. It's a mathematical formula. I mean, that's what it is. It's binary mechanics is simply that. Just
so. What do you want? Something in words only? It sounds to me like you're saying you want something in words only.
I want something.
In other words, I call that science poetry. So if you want to go in that direction, you're in an entirely different playing field. Okay. You're not even in the stadium. Okay.
Okay. So
where the game is being played.
Yeah. Okay. So it's strictly mathematical, and like I said, it moves from here to there only because that's what your equation says. And as far as the fundamental.
Well, again, you want to know why? You want to know why Jack and Jill went up the hill?
No, I don't want to know why Jack and Jill went up.
Well,
no,
maybe there was one up there.
I don't want to know games. I want to know, what the cause and effect is. In an elastic medium, you have waves because
you want
there's
to
a
know
bond
why
between,
these particular equations are correct.
Because they're based on,
if the particular equations,
because they're based on experimental results.
Go ahead.
Bingo. He's I don't know. He's supporting maybe, but there is energy coming into all energy entities and flowing through it. So maybe that's just one way of resolving the matter. Probably we don't disagree with that. But we are coming to an end, Cornelis. So
Okay.
Thanks for raising that point. Thank you very much.
Okay.
And,
thank you. Sorry about the technical problems earlier, but thank you, Ian. Thank you.
At least we got in at the end. Thank you. Thank you. I always prefer to have the person,
Thank you.
particularly if he's available in the green room. That's why we're having a problem with Carl, hopefully, because he has a number of things that I'm sure he'd like to say, but he just can't get in. So, Jim, what I'll do, if it's agreeable with you, as is customary, I'll put myself down. I'll give you as long as you want, a minute or two, or even up to 5 minutes, to summarize or say anything further, or anything that's arisen because of the discussion or the questions, or supplement anything that you said already, or talk about anything that might be done in the future. And then I'll come back and officially close the meeting. So I'll give you the floor again entirely for the moment.
Well, I want to thank everybody for their kind attention to my thoughts. And I hope that this has been interesting to you, and perhaps you want to pursue it a little bit more. In terms of these basic questions, like what Cornelis was raising, the questions of why, why does, the sun exist? Why does my arm raise when I raise it? And so forth. These are pretty much philosophical things, and it's like saying. I just wanted to make that point and to thank everybody. Thank you, Ian. So I'll turn it back to Ian. Thanks, everybody.
Well, thank you very much, Jim, for that brief summary. I put everybody up instead of removing him, and then let me see now. Yeah. Right. Well, it devolves upon me, as usual, to engage in what is simultaneously and paradoxically a pleasurable experience, and one tinged with some regret. The regret is stopping the conversation, because we could certainly go on for another hour, and indeed for very much longer. I hope over the coming period of time we'll come back to some of these questions. And in fact, I do earnestly hope that Jim will come back in the near future. As I say, we have a second cancellation coming up very soon, and I'm not going to push him to fill that, but if he could, I'd be more than delighted, because otherwise I think we're going to have to play a few videos and just have a few little chats ourselves. Although I do have a full program coming up for the next until the beginning of July. Don't worry about that. I just have one or two gaps here and there. I have one gap coming up soon. But I'd like to thank Jim very much for filling the gap today. And indeed, the pleasurable part of it is that I can I'm in a position to express the gratitude of the CNPS and all the participants through Facebook and through YouTube and through the green room, although obviously we've had some difficulties in getting people in today. I always like listening to Jim. He's a very sort of logical thinker. He's been involved in, sort of vetting proposals for, I think, research projects and so on. And he always says, look, just look at this and put it down clearly and do that. And he always gets to you quickly if you sort of are asked a question and you start rumbling on instead of dealing with the point. He said, no, deal with the point and then come back later if the questioner is not satisfied. And I think that's a very good way of looking at things. So I'd like to thank him very much on behalf of all of us for having taken the trouble to give us a further presentation on these brand new videos. I understand these are additional videos that he's produced, because he has quite a panoply of videos, and he's produced. These are brand new. The first one, actually, the 15-minute one, is just hot off the press. So we're the first probably to have seen that. And I'd like to thank all of you for having made the interesting comments and asked questions. So we will be coming back to many of these. And in fact, I'm in the enviable position as well to be able to report that I have been party to a certain extent in introducing people. So some of our regular people have been introduced. Jim is corresponding with some people like I think Stefan Gift and Denny and so on, and corresponding in response to things that have arisen because of recent presentations. So I'm delighted to be able to have brought people together. We don't all have to be together producing hundreds of questions. We can maybe have, one-to-one correspondence between people, and I'd encourage that. So thank you very much again, Jim, for giving us your time and for agreeing at such short notice and producing material which is as I say, rather turgid, I must confess, but is now there for all times, and people can go back and look at the slides and the videos that he's presented. So I must end the session now, thanking you all again and thanking our speaker, and wishing you, wherever you are on the earth or in the universe, a very good day. Good day.